So please welcome Kandrika, who'll be presenting about the smooth package.
Okay, so so my talk today is called forecasting smoothly with smooth package. So this is basically Ivan's package, not my package. So all the credit goes to Ivan Tretunkov because he basically creates smooth packages in R from scratch. Basically, do the develop the exponential smoothing first. Exponential smoothing, and then he extended to some extent, and then he tried to do he tries to generalize things into Adam framework. So that's basically what I'm going to talk about Adam here. And me, Kandrika, is an avid and advanced user of Smooth because I use Smooth quite often for my research mostly. And I quite know inside out, especially as a user of smooth packages. And then, Ivan told me that I'm possibly the third person in the world that knows the codes in smooth packages, basically. Apart from his, and then Philotas. So in general, how do you basically forecast? And you need to use a statistical model to use. Then you can usually just have spontaneous smoothing, or we can use regression, we can use ARIMA, or we can use any favorite forecasting method. So all the textbook that we have here says that, okay, ETS and ARIMA could be a different model, but then it is basically formatted differently. But then in general, it could be combined into one framework. So in this case, smooth package uses single source of errors test-based model to do the forecasting. So in the smooth packaging CI, it basically implements the dynamic model using a single source of errors as state-based model. It has a lot of functions there. For example, Adam, ES, SS ARIMA, so seasonal ARIMA, seasonal ARIMA, and multiple seasonal ARIMA, and then simple moving average, complex exponential smoothing, and then generalized something. Remember, I don't really use it, but but the others is just that he basically used the single source of error model and then try to format it in different ways. So they have, and then he basically have a different names for it. And Adam tried to encapsulate it into one big framework. So what makes smooth function special? It's because of the core function itself and several key principles. So this is something that the main point of this presentation is that I will talk about the core of the Adam itself, how Ivan basically try to reduce the size of the matrix into a smaller one, and then some key principles that are quite useful, especially me as the advanced user. I find it quite useful, especially if I want to set up an experiment, given a specific value of parameters, then this is very handy. So the first key principle here is robustness, because again, this is a generalized approach in SSOE forecasting model. So then in the Adam function itself, it requires some checking, thorough checking. So then the Adam function itself makes sure that the specific model works and produce adequate result in any situation. So for example, if I want to use ETS framework in Adam, then I just need to put something in in the parameters or the argument Adam function. So then the Adam function would check whether whether I want to do ATS or not. So for example, yeah. So then if yes, then okay, let's do it. If not, then okay, you might need to do something else. And then Adam would just tells me that okay, you need to put different parameters in the function itself. So the second one here is the flexibility, because the user have the ability to fine-tune the model to changing the parameters, setting up, for example, if I want to set the initial value for specific initial value fixed, right? And then I want to estimate these parameters, I can do it. And then how we can also set up different initialization. So for example, in ETS, we have the optimizes initial value, or what we can do here is to do backcasting, or the combination of both of them. We are still working on it, but it's possible to basically do backcasting first and then estimate the initial value. So then if I want to, for example, produce a specific value or smoothing parameters, then again, I can just put the specific value in the Adam function to produce forecast according to specific value. So it's very flexible. And then I can also, you can also do estimation using different loss function. So you can also define your own loss function instead of using MSE or using mean absolute error. You can create custom function, custom loss function. So then, yeah, it can adapt to your needs. So then the Adam here also can be applicable to different cases. So because the general framework here is state-space SSOE, single source of error state-space model. So then it can transform into different types of models. So in this case, then it could be a regular demand. It could handle regular demand. It could handle intermittent demand. It could handle multiple seasonal, multiple frequency. It can handle exogenous feature. For example, if we know some dairy variables in there, we can identify whether specific date, specific the point is an outlier, and then try to trade it inside the ETS or state space ARIMA. And then we can also add some conditional heteroscedasticity here. So this is the Adam here, because they can use the single source of error status model, and then can be transformed into different types of model. And then the last one here is data agnostic, because it basically can work with a factor, TS, zoo, data frame, tsibble, etc. So this is the framework of Adam itself. It's captured in this book. This is written by Ivan himself, and it's available online for free as well. So yeah, you can have a look at it if you are interested in understanding the framework Adam. So as I said before, Adam here encapsulate all of the functionality, encapsulate the most general function in smooth, because then Adam here, if you use Adam, you can also do ETS, you can do ARIMA, you can do regression, or with a different distribution, and also with different features in that. And why is it important? Why Adam is important? Because I think it's quite very useful for doing for research itself, right? And then prototyping, experiment. So that's why Adam here is very important. It's useful. It's instrument for benchmarking, experiment, prototyping, and also research. So that's basically the introduction of Adam itself. And then what I was going to talk about here is the core function of Adam. The critical capacity of Adam. So basically, I will present you some equation for this single source of error model. And then I will talk about how basically Evans implemented into R with C++. And then I will give you some example in ETS, ARIMA with smooth, and also some advanced modeling with smooth. So this is the ecosystem of Adam. So I'm basically stealing from Philota's presentation here that what I'm going to talk about is the core of the Adam itself, right? So how basically smooth here fits the data into the model. And it can be transformed into different ways of modeling. So then it can transform into the ARIMA, ETS, or common smoothing, depending on the how the users define Adam itself. Okay. So in nutshell, Adam relies on this state space model, right? We have the measurement equation where it's, and then also for the first equation and the second equation is this transition equation. So the innovation here is basically the factor L. Factor L here is the factor of flex, and I will discuss it in the next few slides, how we basically can reduce the number of the size of the metric itself. So it makes the calculation a lot easier, and also it enables us to increase the number of states in the SSOE, so then we can have more components in the model itself. So what I'm thinking here as SSOE is basically like a Lego, where we have a specific pieces of Lego, and then we want to create some building depending on what you need. Here, for example, we have a representation of house, and then inside these pieces of Lego here, there are some dynamic behavior in the dynamic pattern that goes inside these pieces there. So then this whole Lego here can be represented as the measurement equation, and then something inside each pieces there is the transition equation. So then if we can build different types of houses with different features on it, so then we basically have different model that has the same features, which is basically this SSOE model. So in this case, let's break it down into ETS AADA. So we have we have additive error, dampened trend, and seasonality using Adam framework. So I will try to compare it between the conventional one, right, and then the Adam framework. So in this case, we are using the conventional one from Augmented book. So this is basically the representation of the matrix where we have a lot of So for example, here we have positional components. We have many rows to represent different legs of frequency, right? Because we want to define it when we this t and t-1, t-2, t-3, and until t-m+1. So this is explicitly shown in the matrix. So what Adam does here is basically to create another factor, to basically create a helper to find a specific value for specific legs. Okay, so in this case, F, the transition matrix here becomes smaller because what it does here is just find the specific, just represent the seasonality, and then seasonality, and then it will look at the specific value at the leg m. So let's have a look at the example here. So the matrix with so here, for example, we have a state, we have a level, trend, and seasonality, right? And then we look at the time when t-1. So then because we know that the factor for the level for the L is equal to 1, then it's better we just look at one period before LT. And then also for the trend as well, because the lag here is equal to 1, then it only looks at one the previous period. And then for the seasonality, because we want to look at the M period before ST, then it's basically tries to look at the S minus T months. So what it does here is basically try to is defining where to look at from the previous value. So in the previous equation, like this one, this metric explicitly shows the lags of the seasonality, but then in this case, in the Adam function, in the Adam framework, it tries to look at the lags depending on using some feature or helper here to determine where to look at instead of moderate in the matrix. Then it is transformed into a helper to determine which element in the matrix we are looking at. So because we didn't really because it doesn't really explicitly model or design the matrix itself, right? So that it requires some for loop function because it needs to look at a specific value for a specific observation. Then using for loop in R would be slow. So then what if one does here is to use C++ with RCPP and SRCPP ARIMA below, and this is what the OR function is. So the goal function is basically try to fit the data into a specific model. Okay. Given that we know the value of X, the value of W, value of G, the value of V0 and L. Okay, and it recursively applies model to each observation, and then the fitter here we return the states matrix, fitted value, and error term. So the C++ here just try to fit the data into specific model given that we know the specific value of F, W, G, V, O, and L. The other function will determine whether we want to predetermine the value of this matrix or this vector, or we need to estimate some value inside of this matrix or the vectors. Okay, so that's basically the core function in the C++ for fitting the data into. Yeah, so for example here, see the core is written in C++, and then the R itself, the wrapper in R, will check the parameters, we design the necessary matrices, we'll fill them the parameters to calculate the value of the loss, select the components in order, prepare the output, etc., etc. So the core here is just to fit the data into specific model that is predefined by the user, right? By the end user. And then the R itself, the environment of the smooth package there, we check the parameters, whether the parameters here fits to the necessary or okay to fit us the data into a specific model. and then design the necessary metrics and then fill in the specific parameters, or whether we want to estimate those value in the metrics. Okay, and then Phil will explain this more in detail in the implementation in Python. So the example that we got here is that we have ETS with predefined parameters. So basically, we have a specific data. We put the ETS AADN. So there is no seasonality there, additive errors, and also additive time trend. And then we set up the persistent value here as the 0.3 and 0.1. So we don't really estimate the model, right? We just plug in the number inside the ADAM, and then they will do the fitting basically based on this specific predetermined parameter. So we can do it because then in reality, for example, if you have short time series, using having smaller smoothing parameters will benefit instead of having estimated one, just because it just try to fit the mode, try to fit the data, so then the smoothing parameters would be higher, then the forecast would be volatile, etc., etc. So what Adam does here is that we check the data first, check the model whether, okay, this is ETS, right? Because it includes the AADN, okay, it's ETS. And then what is the parameter? So if there is nothing there for the persistent, pi, and then initial, then they'll be estimated automatically using a simple likelihood. If, for example, it's predefined by the users, then it will use the specific value in the ADAM to fit the model and produce the forecast. So in this case, there's no estimation at all because we define everything. We define it. And then because of the user input this number, then the wrapper in R will create a matrix that includes all of the number in the matrix there. And then this matrix will be inputted into the fitter in C++. They do the fitting, right? For each observation. They create, and then it result in this specific states, result in the y hat, the fitted value, result in residuals, and then it will produce different, and then the R wrapper will capture that and then transform it into something else, basically the output of the model. Okay, and then, so that's if we predefine the parameters. What if we estimate the parameters? Again, we just need to define the model here as x, z, x, z, meaning that we are trying to find the model from either additive or multiplicative errors, and additive trend, and multiplicative or additive seasonality. And we use loss function of log likelihood in this case. So we don't really define. We don't do predetermined parameters. We ask Adam to estimate the parameters using likelihood. And then what it does here, check the data and parameters, right? Because we want to check whether the Adam needs to estimate the parameter or not. In this case, yes. And then prepare full of the model, design the metrics for each model, fill them, use it for function, estimate the parameters, maximizing likelihood, and then return the information criteria for models, select the best one, and then, the best is another history. So that's basically what Adam does in this step-by-step. So this one of the example where we have, I think this one is the monthly data F5. One of the M5 data set, monthly data. We use we estimate it, and then we use we produce one to 12 step ahead forecast. We keep the holdout sample. We assume that distribution is normal distribution. So then we end up with this model. We can estimate this alpha and gamma with specific, and then result in AICC. So then we can find the best model, and then we can also calculate the RMS SE for 1 to 12 step ahead forecast automatically from Adam function. Okay, and another example here is want to use multiple seasonality, so in this case, assuming that there could be different seasonality in there, so we can also model it here using auto ARIMA. Because we don't really define whether it is AADN or MAN or etc. Then yeah, so it uses because it's ARIMA, so sorry. Yeah, because it is ARIMA, so then it automatically select the number of whether it's seasonality or not, whether the number of flags, number of moving average, etc. Again, in ADAM, we can in the inside of the model here, we can have the split. Yeah, we can have the test set and it split the training and test set in the model, right, and produce the RMSSE from the model ARIMA model here. Another one here, because we produce the number of we reduce the size of the matrix, so then we can add more components. We can add states in the framework, so then we can have ETS with ARIMA. Let's imagine this is just a very toy example when we have ETS and A and plus the ARIMA components. In this case, just AR1. We can do it by defining the ETS first, and then have an order 100 means that we add the AR components in the ADAM framework. So in matrix wise, it's basically the first two here is the ETS, right? And then the last one here is the AR components. The last one here is when we have a dummy variable. I don't have much time anymore. So basically what it does here, so if we, for example, do the usual analysis using automatic selection, it finds that, okay, also in 40 outlier, and then ADAM will detect it as an outlier, right? Because we define it as a level of 0.95, the outlier here is used, so that it will treat it as the outlier, and then do some estimation there. We use ETS X, M, and M. But in this case, in this example, it's not worth it because the AIC is not better than the previous one, and also the holdout sample is not better than the previous one. So in the matrix itself, the measurement equation will transform into this bit. So it will different observation have a different value for the factor. So in this case, for the WD14, we define it as 1. So it's just like activate whether this is an outlier. So then so then there is some the dynamic components of it is defined here, and then it only applies for observation 14. In conclusion, Smooth was designed to make a research in dynamic model easier. Some argue that it's not easy to implement because it's very big. It's very it encapsulates everything, so then it's sometimes confusing. But it's very nice for research, I would say. It's a default setting characteristics of robustness because it requires many checks inside it. And then it could be implemented in the regular intermittent demand, multiple frequency, promotional modeling, and also it's flexible in the innovation because we basically publish a paper about using shrinkage estimator for ETS just because we want to make more deterministic states rather than stochastic states, and we can use it using custom loss function. And and then we can bring this functionality to Python, and Philotas will talk about it later after this talk. Okay, so thank you.
Okay, thank you very much. And who better to be a discussant for this than Adam? Adam is also a good discussant for this. He's recently been working on C++ for his own software.
Okay.
He's prepared some slides, which I'll put up now. You can leave your computer plugged in.
Sure.
The slides are here.
Is Ivan here?
You can leave it there.
No. Is Ivan here? Because he's
Ivan is online.
all right. Okay.
Yes, I'm here, if you can hear me.
Yes, we can hear you, Ivan.
Okay. Cool.
Thank you, Kandrika, for the great presentation. And so first, congratulations. So your package is very general and has very flexible, and be flexible to apply just different types of time series data. And it has many nice features like variable selection and model type weighting, and etc. So, and you also have the comprehensive resources like the open source textbook online and also the VNets. So my first question is one point about the code structure. So after I take a look at your C++ code, I realized that in your code so for example, for the item forecaster, you didn't export it to R. Instead, you wrap it with another C++ function and then export the wrapper instead. So I wonder what's the benefit of doing this?
Give it a second.
It has to do with Hammurabi bounding this.
Ivan,
Right.
Ivan, did you want to comment on that?
I can actually. Thanks a lot for the comments, all quite valid. About the RCPP thing that was originally developed back in, I don't remember, 2015, 2016. And I think their code base have evolved a little bit. So in the end, there are some wrappers left. I amended some of them, but I'm not sure whether all of them are up to date. So that's a very good comment, and thanks. And in general, I would answer also that any help is welcome. So if you can provide some guidance and so on, that would be great. Thank you.
So I think nowadays, if you just export the item forecast function, it should also work automatically.
Yeah, sounds good.
And so my second question is also about the code structure. So in your R function CS, there's one function filter inside the CS function. So I wonder what's your decision of why do you put filter inside CS? Why don't you move filter outside and export it, etc.? So what's your decision between making a function local inside another function instead of making it a local function itself?
That's also a very good question. The main motivation here, actually the main motivation for doing C++ was to speed things up because R is pretty slow. And the narrowest bottleneck in the whole thing was the for loop for applying the dynamic model. So this was implemented in C++ to make things faster. All the others, I didn't find any improvements if I implement stuff in C++. So I just left them there because that makes things a bit easier. And plus Phil will talk also about implementation in Python. So this design decisions was actually quite good, I would say. So two things here, right? First, speed for the feature, and second, it's just easier to read code, I guess. And OpenSci, yes, but I haven't had much time to do that. So any help is welcome. Again, thank you.
Did you have anything to add to that, Kandrika?
No.
Okay, so lastly, so first, congratulations on the very comprehensive textbook. It's very helpful. And so one comment I will make is that it's also very simple to generate a package download site for the README file in your package, so that it can also serve as a helper online for other people to use your package. And then lastly, my question would be, do you plan to publish your archive paper on this package to maybe JSS or PR journal? If so, what do you consider? What things we will consider to add in this archive page?
Yeah. Thanks. So about publishing, it was rejected from Journal of Stat Software. Haven't thought of submitting to our journal. That could be a possibility, but I don't fully also understand what you mean by adding material. Like what, do you have any suggestions?
So the reason why I ask is because we also want to maybe publish our archive paper in GSS or the R journal. So I want to learn from your experience. That's why. And about adding materials, maybe adding empirical examples or theoretical details. That's some things that will be.
Yeah. Sounds reasonable. The issue, if I start adding technical details, I'm afraid this will become a book. But in general, yes, that makes sense. We will think about submitting to our journal. Thank you for comments.
Thank you, Ivan, for the admissions.
Okay, and were there any other questions from the room? Yeah, so kind of a beginning question about the SSOE as a standard formulation. Does this mean, like, also given that as the fixed initial state, does this mean that the forecasts from this package are kind of like homoscedastic distribution forecasts?
Well, I think in other function you can also add some heteroscedasticity aspect of it. So it implements some LSS, for example, that models this the sigma, and the sigma would also change over time as well. So it also encapsulates that, and you can also add that function.
What is that like based on? Like that the framework? Is there common filters?
Oh, so okay. So for this one, it's not Kalman filter, but it's a single source of error. So we assume that for each state in the model has a single innovation. So we don't have many innovations there. So yeah, that's basically the SSO.
Yeah.
So it's not Kalman.
So you mentioned something about common SS association. Okay, sorry, not my yes, heard.
No, I didn't mention Kalman filter before. Yeah, it's just a single source of error, not multiple source of errors.
Nice question. So two things. One is I'm currently the executive editor-in-chief of the R journal, and I would welcome a paper from Ivan on the smooth package. So feel free to send it my way. Second comment. So the Atom function still has the interface has pre-specified models. But what if I have my own single source of error model with my own F matrix and G vector and so on? Is it possible to export some of those lower level functions so that I can build my own SSOE model in the package?
I try to answer that question. Maybe if I can edit later. Because I tried to find a way to, basically I want to create a SSOE function, but I couldn't do it enough. So yeah, I don't think there is especially for the measurement metrics it's not. I find it quite difficult to, as a user, as fund user, to set specific W or specific F. Fine.
Yes. So yeah, you could create a separate wrapper for the engine to make a new function. And by the way, thanks for the kind words, Rob. But there's also a function which I've written some time ago, which is called Generalized Univariate Model. And this is supposed to be a paper with Nikos Kourentzis, but we haven't finished that just yet. which actually is a flexible architecture, which allows you to define any transition metrics or measurement with a variety of parameters inside. So there is this functionality, but we haven't done any proper work on that. Yeah, thank you.
GUM. I think GUM, right?
GUM, yes. GUM.
Yeah, GUM. But yeah, so that's one of my predictive one perspective how do we define FNW.
Okay, please join me in thanking Kandrika again.